Okay guys, now we are coming to the second subject on analysis of structures. So far what you have learned is analysis of statically determinate structures. Statically determinate structures means that you can solve the structure by deriving equilibrium equations, which means that any unknowns in the structure can be derived using these equilibrium equations. But if you look at in real world, in real structures, there are very few structures that can be classified as statically determinate. Most of the structures are statically indeterminate. And there are some reasons why these structures are statically indeterminate. One of the main reasons that they are statically indeterminate because we need to reduce the stress on structural elements. So how can we reduce the stress on structural elements is by reducing the span of the structure. You can achieve that by increasing the size of the element. So there are various ways that a structure can be approached in a way that to reduce the stresses. And the maximum stresses in statically indeterminate structures are generally lower than those in comparable determinate structures. So determinate structures have the required very minimum supports. Means that a failure of one of the support could cause a collapse of the structure, and that is something that is not preferred. So in real structures you have more supports than the required amount of supports. Then those structures fall under a category called statically indeterminate structures. So there are many advantages of building an element or having an element that is statically indeterminate. The challenge is you can't simply derive equilibrium equations and solve this structure or solve the beam or solve the frame. The reason is there are more unknowns than the minimum that can be resolved using equilibrium equations. Now we are going to look at how can we approach statically indeterminate beams. So these lectures are confined to statically indeterminate beams. Now let me show you an advantage of statically indeterminate structure. So now this is on your left hand side is statically determinate. This is a statically determinate beam, and this is a statically indeterminate beam. How this has been converted to statically indeterminate beam? Here you can see that there's a pin here, there's a roller here. Now if I convert these two supports to fixed, then it becomes statically indeterminate. The reason is, if you take the statically determinate structure, how many unknowns you have? You have 3 unknowns. But if you take this one, you have 6 unknowns, and you can't resolve 6 unknowns using standard equilibrium equations. So in such case, you can plot the bending moment diagram. See, when you plot the bending moment diagram, the bending moment, the maximum, so maximum bending moment is M max is equal to WL squared over 8. But here if you look at the maximum bending moment, which is at the support, WL squared over 12. So this one has lesser moment than this one, but the same loading. Only difference is you have the support conditions changed and may converted this to statically indeterminate. And also if you look at the deflection, say here the deflection is delta max So here it is given here 5W L to the power 4 over 5W L to the power 4 over 384 EI. And if you look at here, the delta max is WL to the power 4 over 384 EI. So the statically determinate structure has 5 times more deflection than statically indeterminate. So because of these reasons, so there is, if you look at the determinate versus indeterminate, here the lower moment, so here higher moment is high, M max greater than M max here. So M max determinate indeterminate, which means stress greater than the stress here. And deflection is high. Deflection is low. So these are the advantages of statically determinate and indeterminate structures. So because of these reasons, more and more the real structures are statically indeterminate. So now if the structure is statically indeterminate, how can we solve this? So some more advantages of statically indeterminate structures are greater stiffness. We have seen that the deformation is low when you have fixed support conditions and when the structure is statically indeterminate, and when the redundancies. So this is something that I mentioned earlier, that if you have supports, the bare minimum supports, what happens is when a support fail, the entire structure could fail. But in a statically indeterminate structure, there are redundant supports. So in statically indeterminate structures, if properly designed, have the capacity of redistributing the loads when certain structural portions become overstressed or collapse in case of overload due to earthquakes, tornadoes and impact loads. So due to these reasons, these statically indeterminate structures are preferred. And when it comes to analysis of these statically indeterminate structures, there are two methods. One is force method, other one is displacement method. So the force method, I'm not going to touch about force method, but you can go and see in the book there are discussions on the force method. The force method has some limitations. That means, if you have only one additional unknown, then you can solve that using force method. But the stiffness method is more versatile. So we are going to look at the stiffness method. So in the force method, the unknown redundant forces are determined first by solving the structure's compatibility equations. Then the other response characteristic of the structures are evaluated by equilibrium equations or superposition. But what we are going to look at are displacement method. And the displacement method, there are two. So there are two displacement methods. Displacement methods, we have two way. One is slope deflection method, then the second one is moment distribution method. So we will discuss these two methods, and as part of this analysis of statically indeterminate beams. And you should understand that it's very, very useful, these two methods. And even if you go out as engineers and start practicing in a company as structural engineers, these two methods still be useful. So you need to pay a good attention on learning these two methods, because they are really helpful if you are going to be working in a industry as a structural engineer. So in this lecture we are going to go in detail on slope deflection method. So it's a stiffness method, an alternative approach that can be used to analyze indeterminate structures is termed the displacement method. So it's based on a stiffness criteria. Unlike the force method, the displacement method, in displacement method, the unknown displacements are determined first by solving the structure's equilibrium equations, and the other response characteristics are evaluated through compatibility considerations and member force deformations. If you look at the slope deflection method, it was first introduced in 1915 by George Money. The method takes into account only the bending deformation of structures. Although the slope deflection method is itself considered to be a useful tool for analyzing indeterminate beams and frames, an understanding of the fundamental of this method provides a valuable introduction to the stiffness matrix method. So based on stiffness matrix method, we have several finite element softwares that is used in structural analysis. When a continuous beam or frame is subject to external loads, internal moments generally develop at the end of individual members. So if you look at a beam, say if you have some 3 supports like that, then when you load, due to this loading there are internal moments induced in the member. So that is why you plot these bending moment diagrams. The slope deflection equations relate the moments at the end of the member to the rotations and displacements of its ends and the external loads applied to the member. So now, for example, if you take this beam, this is one segment, this is another segment. Now if you take the segment 1, you have the reaction here, and then you have the load. You may have some moment, axial force and shear force. Now this slope deflection equation takes this segment and it relates the moments. So it relates this M at this end to the displacement and rotation. At these ends. So to derive slope deflection equation, let us consider an arbitrary member AB of the continuous beam shown in figure below. So if you take this figure, this is a random section which is loaded by a point load and a uniformly distributed load, and once it's loaded it takes a shape that is the deformed shape. So earlier it was the horizontal element, now it is deformed, rotated and deflected. So now based on this we are going to develop the slope deflection equations. So if we consider this deformed beam, we can see that there are some internal supports and some settlement on internal supports. You can see that originally it was on this position and now it has gone down a little bit. So this beam incorporates point load, uniformly distributed load, rotation at joints, deflections on the beam and also settlement of the beam. So now if we take a segment of this, a small segment of this, then we can define that small segment using this sort of a setup. So here you can see that there is a support A, there is a support B, and there is a MAB and MBA. So since this is AB, so MAB counterclockwise, MBA counterclockwise moments, uniformly distributed load and a point load and the length L. And if we consider EI is constant, that is flexural rigidity EI is constant. Now if we develop a set of equation that some way in a way can relate moment, slope and deflection and settlement, and that will help us to derive a set of equations that can help us to obtain these moments. So when the beam is subjected to external load and support settlements, the member AB deforms. So here you can see that there's A here and there's a B here, so it deforms. So the member AB deforms, and when it deforms, you can imagine if you keep a ruler and if you deform the ruler, you can think that you can see that there are some moments induced at the supports. Okay, just get a ruler, a big 30 centimeter ruler, and keep in your hand and tend to deform the ruler, and then you can see that there are some moments there are some restraints that you have to provide using your fingers to prevent the rotation. So that is what happening inside a beam. So the Hibbeler diagram, an elastic curve of the beam is shown here. So here you can see that Hibbeler diagram is shown here and the elastic curve is shown here. Now as indicated in this figure, double script notation, there is a double script notation, that is, if you look at this one, this is delta AB. If you look at this one, this is delta BA, and the moment here is MAB and MBA. So double script notation used for end moments, with the first subscript identifying the member end at which the moment acts. So if you consider AB, the first letter A stands for where the moment is acting at A, and B stands for the other end of that segment. Okay, so MAB denotes the moment at end A of member AB, whereas MBA represents the moment at end of B of member AB. So now we are going to derive a set of equations using this analogy. So also as shown in figure, you can see that there is a theta A. There is a rotation theta A here. There is a rotation theta B here, and then you have a deflection delta here, delta relative translation. So here this delta marks relatively, earlier it was on the same line, now compared to B, the A has settled, or compared to A, B has some movement. So that is the settlement. Say now you have a deflection of a beam is different from settlement of a beam. Now say if you consider a beam like this, so then when you have a load acting on the beam, then the beam deforms. So this is deflection, this is deflection. Okay, this is deflection, this delta. But on the other hand, what happens is, say if you have a beam, then under the action of load, what happens is, say if this support, say if you consider this is as a column, and if the column if this column settles, so it settles means it goes down a little bit. So in that case, what's going to happen, the beam is going to take a shape like this. Okay, so the settlement, so this support's staying at this point and this support is now here, so it has to bend like this. So this is the settlement. Okay, settlement of support. And so now this delta denotes the relative translation between the two ends, and the angle psi, there is angle psi denotes the rotation of the member members chord due to the relative translation. The chord means this is the axis. So the axis is rotated by an angle psi. So there are three angles involved here. One is due to the loading, there is a rotation theta A. Due to the loading, there is a rotation theta B, and due to the settlement, there is a rotation psi. Okay, and the psi is defined as delta over L. Okay, because if you take small tan, so tan psi is delta over L. Okay, so this is delta and this is L, so that is tan psi. For small angles, tan psi is equal to psi, so that is psi is equal to delta over L. Now we have to derive a set of equations so that can bring us these set of equations. Okay, so now we'll see how to derive this. So now if you take here, we need this conjugate beam method. Okay, that is very useful here. Now if I consider a beam, that same beam AB, and this is a continuous beam, that means this is not pin jointed, so it's a continuous beam, so you have to expect some moment to be carried here and moment to be carried here. Now I apply a moment MAB. Okay, I apply a moment MAB. So now this MAB is going to have some moments acting on it. Okay, so there is a moment MAB, and if I have this joint, say if I have this joint fixed, so I'm taking an analogy, so here is a pin joint, here is a fixed joint, so I apply a moment MAB. Okay, so now I have to find the effect of this MAB at this point B. Okay, so that is what I need to do. So to do that, what I need to draw the bending moment diagram due to this moment, and using conjugate beam method I can find the slope and deflection. Okay, so let us see how can we do this one. So this moment is going to rotate this one in counterclockwise, so this is going to take a shape like this when it rotates, so it's going to take a shape like that, and here the rotation is theta A, and here there is no rotation because it's a fixed support, but to keep it fixed, so it will have to have another moment MBA. So these are two moments, MAB and MBA, and this is a pin joint and where the rotation occurs. So now if I translate this into a conjugate beam, you know that if it is a pin support, in a conjugate beam it's going to be again a pin support, and if it is a fixed support it's going to be a free end. The reason is, in a fixed support there is no deflection, there is no rotation. So if you consider rotation and deflection in conjugate beam, rotation means shear force, deflection means bending moment. So there should be, at point B there shouldn't be any bending moment, there shouldn't be any deflection, so there shouldn't be any bending moment, there shouldn't be any shear force. So if that to be the case, it should be a free end. Now this MAB, if you draw MAB, it's going to be it's going to be a moment. It's a hogging moment, so it's going to be MAB over EI. So MAB will have an effect like that. So the bending moment is it's going to be like that. So you can, so this is MAB EI, and MBA is high and low here, so it's going to be that MBA over EI. And here there is a reaction downward, because downward or upward, the reason is it's rotating counterclockwise, so it's a positive shear, so the reaction also upward, that is theta A. So here the shear force theta A is equal to the actual rotation A here. So the upward force is theta A. So now you can mark the force, and this one acting downward. Okay, so now this is the conjugate beam theta A, and MAB over EI and MB over EI. So now if we take equilibrium conditions, okay, if you take equilibrium conditions, so if you balance all the forces, so this is in equilibrium, right? So if you balance all the forces vertically, sum of all the forces is 0 vertically. Okay, so you have theta A plus the load due to the upward force is half into MBA over EI into length L minus half into MAB over EI into L is equal to 0. So that is one equation. Then the second equation, you take moment by A. So by A, if you take sum of M is equal to 0, okay, sum of M is equal to 0, which is say half into MBA over EI into L, that is the load, and the distance to that load is 2/3 L, because this is L. I am taking moment by this point A, so it is 2/3 L for this top part of the load. Then this load cancels off theta A because it's acting to the point, then minus, you have the other one half into MAB over EI into L into 1/3 L is 0. So now this is the second equation. So here you cancel L, you cancel the other L, and half cancels off. Then you get PI also cancels, so you get 2BA, 2MBA. Okay, so 2MBA is equal to MAB. Okay, so MAB. So MBA is equal to MAB over 2. Okay, so this is, now this shows, now for example, if we apply a moment MBA, and to prevent the rotation at the far end of the beam at B, you need to have a moment, half of that moment we applied to keep that from rotation. So that's the meaning of this. Then so you can have a equation between the theta and MBA as well. Okay, so if you get this equation, so theta A is equal to half is equal to half MAB over EI into L minus half MBA. So MBA we can replace with MAB. So MAB over 2 1 over EI into L is equal to 0. I'm replacing, not 0, I'm replacing this MBA with MAB over 2. Okay, so now here we have MAB over EI into L half minus 1 over 4 MAB over EI into L. So here the theta A is, so half minus 1/4, so it's MAB over EI into L. Okay, so that is the value of theta A. Similarly, if you do it for the other, say if you keep the, say here A, B, so if you keep A fixed and here if you rotate it by an angle theta B, so then it takes a shape like that. So this rotate by theta B counterclockwise. So if you do the same, okay, so B here, A is there. So if you take the similar case, here you have MBA, here you have another counterclockwise MAB. You should remember that, okay, if you apply a counterclockwise moment to rotate this by theta A, then you need another counterclockwise moment to keep that from rotate. Okay, so if you do the same, if you do the other way, like keep A fixed and rotate B, then you will again get something like MAB is equal to half MBA. Okay, so that you will obtain. Then you also will, here this is 1/4, right? Then also you will obtain theta B is equal to 1/4 MBA over EI into L. So it's similar to what we have derived earlier. Okay, so these equations you will obtain if you rotate the other end by theta B. Now the third equation we have to derive is for the deflection. So the third one is the settlement. So now if you look at the beam, and we consider both ends fixed because we don't have any rotation now, and suppose if one of these supports settles, so then the new position of the beam would be this. Okay, so it settled. So let me draw a dotted line. So now the new position after the settlement would be this. Here the settlement is delta, and this can be considered as a deflection also. And now there is no rotation to prevent this. So when you can just imagine with the ruler, you can play around and see how these things are going to work. And if I keep a ruler and fix one side, and if I do not allow rotation, and if I settle the other one a little bit, I can see that there is a my fingers are providing some restraint to the rotation and to keep this slope 0. Here was the slope 0, so then it requires a moment m. Okay, a moment m to keep the settlement keep the rotation 0. So now if I draw the conjugate beam for this, then the conjugate beam, if it is a fixed end, it's a free end here, it's a free end here, and you have an M, this is a hogging moment, so negative, this is a sagging moment, so positive. So M over EI, M over EI. Okay, so that is a bending moment diagram. And so here I have upward force, this M over EI acting upward on this conjugate beam, and this one acting downward on this conjugate beam. Okay, so now this deflection, this settlement, what is in a real, if it is a settlement in a real beam, it is a moment in a conjugate beam. So moment is the moment in conjugate beam is equal to the deflection in a real beam. So now this is the downward deflection. So that is what is that? A downward deflection. So deflection upward positive, downward negative. So if the deflection is downward negative, then the moment should be, so we need to have a moment, so a bending moment, a negative moment. So negative moment means it's a clockwise, okay, so delta, because counterclockwise is positive. Okay, so this is the conjugate beam for the real beam with the settlement. Okay, so now we need to get the equilibrium. So now we need to get the equilibrium conditions for this. So if I take moment by B, so this is A, this is B, so A, B. If I take sum of moments 0, if I take moment by B, so then I have, this is minus delta counterclockwise, clockwise, then I have the load due to this upward load is clockwise, so that is minus half into M over EI into L is the length. So this length is L, and the distance is 1/3 L, plus half into M over EI into L into 2/3 L is equal to 0. So that is the equilibrium condition. So now if I take this one, so delta is equal to, here I have this 2 and 2 cancels off, so ml squared over 3ei, ml squared over 3ei, okay, minus ml squared over 6ei, so that gets me ml squared over 6ei. So now we have a set of equations that relate moment and deflection, or moment and settlement, and moment and rotation. So now I'm going to rearrange these equations. Okay, so before that I need to shift some space to do my, while insert a page, insert a new page. So oh, it's went the other way, so let me insert a new page, okay, good. So now I'm going to mark all these necessary information in red. Okay, so here I have an equation that gives me theta A and MBA and MAB then this equation theta b, so then this equation delta is equal to, so let me rewrite these equations. So now we know that MBA is equal to, so let's write theta A. So theta A is equal to MAB over 4EI into L. MAB over 4EI to L. So this is when you have the B fixed and you rotate, so theta A, when you A, B is fixed and you apply a moment here, MAB. Okay, so if I rearrange this, I get MAB is equal to 4EI theta over L. Okay, and in this case this MBA, so MBA is equal to half MAB, so half MAB. Okay, so here this equation, so in that case this becomes 2EI theta over L. Okay, so this is when you have a rotation at A and B is fixed. But when you have a rotation at B and A is fixed, okay, so you have a rotation at B and A is fixed, then excuse me, so you have something like this. So you have a theta B, MBA and MAB. So here AB. So in this case theta B is equal to, here we have the equation theta B is equal to MBA L into 4 over EI. So MBA L into 4 over EI. So if I rearrange this, it becomes MBA is equal to 4EI theta over L, and MAB is half of MBA, that is 2EI theta over L. And if I consider both ends fixed and the settlement, okay, so if I consider and the settlement, okay, so a settlement, then delta is equal to M L squared over 6EI, M L squared over 6EI. So M is equal to six EI delta over L squared. Okay, so and so these are the equations that relates theta and delta and moments. So here MAB and MBA are same. So here MAB and MBA are equal to M, that is 6EI delta over L squared. So now here we need to get this equation. Okay, some of you can able to see the relevance of this equation. Okay, so now what we need to look at is, okay, we need to look at the formulation. So how to bring this together, okay, how to bring this together is what we are going to look at next. Okay, So we can derive this equation. So the arbitrary section we consider here, okay, the arbitrary section we consider here has theta A, has theta B, and has psi. So everything is there. So now if you have a beam, say you have a beam, so this is the beam AB, and there is a rotation here, there is a moment acting here. So this is a portion of the continuous beam, okay, a portion of the continuous beam. So there is MAB, there is MBA, and there is a settlement. So all these are acting in that beam, okay. So MAB, MBA. So MAB is due to this rotation here, the rotation here, and the rotation here. So it gets a shape, say like what we have seen here. So some sort of a shape. So maybe something like this, or whatever. So here it's theta A, here theta. So this is the angle, it makes theta B. So all these are happening in that section. So there is a rotation on one side, another rotation on the other side, and there's a settlement. So if all these three are occurring, what we need to do is we need to consider all these three conditions. Okay, so we need to consider all these three conditions. So now what we need to say, because of this, if you consider MAB, there is a component due to this rotation theta A, and due to the rotation theta A we have here, that is theta A, here that is theta A, that is 4EI theta A over L, that is 4EI theta A over L. And if you consider MAB, due to theta B here, you will have 2EI theta B over L. So you have plus 2EI theta B over L. And then you have the rotation due to this settlement. So here the settlement, you have so there is this counterclockwise moment M, MEB, and now this is the settlement is delta is ml squared over 6EI, and that is downward settlement. So if the settlement is upward, is considered positive. So in the sign convention it becomes minus ml squared over 6EI delta, because the delta is positive here because we considered this settlement downward, and then here we have clockwise moment, and we derive delta is equal to ml squared over 6EI. But according to the sign convention, the settlement, if there is a settlement downward, then that should be a negative value, because upward is positive. So now this, if you put the sign convention, this delta becomes minus. Okay, so the delta becomes minus ml squared over 6ei. So MAB and MBA becomes minus 6ei delta over L square. So here again, due to the settlement, it is minus 6ei L squared into delta. Okay, so now delta and L, I'm going to relate, I'm going to take you to this equation here. This equation, you can see the psi is delta over L. Okay, so psi is delta over L. So if I replace psi for this 1 delta over L, so I can get this equation as 6ei psi over L. Okay, so if I take this part and here I have 6ei over L and delta over L, and if I replace this delta over L with psi, then it becomes 6ei psi over L. Okay, so then it becomes 6ei psi over L. Then we need to have some moment. Now for example, these all are due to the rotation. Okay, rotation theta A, theta B, but due to the load acting on this beam, and if you consider both ends are fixed, then there will be fixed end moment. So that fixed end moment, normally we typically what we do is a fixed end moment, we mark. So fixed end moment, so when you have a load like that, say on a fixed support, when you have a load, then your FEM AB and here FEM BA. Okay, so now that also should be added. FEM BA is counterclockwise direction, so FEM AB. So if I rewrite this equation, is 4ei theta A over L plus 2ei theta B over L minus 6ei over L into psi plus FEM AB. So here if you take 2ei over L, if you take that out, then you get 2 theta A plus theta B minus 3 psi plus FEM AB. Similarly, if you write MBA, so MBA, due to, say if you look at MBA, then you have 4ei theta B and you have 2ei, so you MBA here 2ei theta A, so this comes to 2ei theta A, and again the same psi value, and FEMBA. So now if I write for this equation 4ei theta B over L from beta theta B component and 2ei theta A over L due to the moment induced by theta A minus 6ei over L into psi minus FEM BA. So here it is clockwise, so it's minus. So that the equation becomes 2ei over L 2 theta B plus theta A minus 3 psi, okay, 3 psi minus FEM BA. So that is the equation here. So you have this here, plus is given because it is considered positive, but in a real condition you will see that it becomes minus. Anyway, we'll keep it plus, but when we do application we can so we'll assume this to be positive and we'll keep it plus, but when we apply in a real situation we'll see that it is negative. So now these are the two equations that we have derived. So this is the first equation, 2 theta theta b 3 psi FEM. So now this slope deflection equation comes from considers the load and the moment induced by the load, and then the rotation, due to the rotation what kind of adjustment to the moment is happening, and due to the settlement what kind of moment is happening. So finally what we are trying to get is we are trying to get the moment. So for example, if you consider a beam, so a continuous beam, so if you consider a section in the middle, there will be M, so M will be there, and then there is a reaction RA, RB, and there will be some axial force and that will be balancing each other, or it could be zero. Then you have the load, so and this axial force as well. So now there are 6 unknowns. So in these 6 unknowns, except the axial load could be mostly 0, and or then if you find these 2 moments, then you can find the 2 reactions. So then it becomes statically determinate, because with 4 unknowns we can't do anything. Okay, even if you ignore the axial load, with 4 unknowns you can't do anything because it is impossible. But if you find the moments, then you end up with 2 unknowns that you can resolve, and you can resolve the beam. So that is what we are doing here. Using this method we find the 2 moments, and then once the 2 moments are found, then we find those reactions so that we can resolve the internal actions or internal stresses in a beam. So the slope deflection equation can be derived by relating the member end moments to the end rotation and chord rotation by applying second moment area theorem. So here we have used the conjugate beam method and we derive this term. So these equations are valid only for prismatic members composed of linearly elastic material and subject to a small deformation. Also, although the equations take into account the bending deformation of members, the deformation due to axial forces and shear are neglected. Okay, so deformation due to axial and shear are neglected in this method. So this is the generic equation. So if you have a beam where one end is N, other one is F, okay, then M and F is 2 TEIL 2 N theta N. So if you are taking on the side of N, you will have 2 theta N, and at the far end will be other end will be theta F 3 psi M N F. So in this, subscript N refers to the near end of the member where you find the moment, and F describes the far end of the member. Okay, so this is how you derive the equation. So next what we are going to do is we are going to do a problem. So I'll upload the problem as a separate video. So the theory covers up to this and deriving the slope deflection equation. So if you have any questions, you can email me at this address .t@iit.lk. Let me write it clear. So gobits@sliit.lk, or you can also send me a WhatsApp message 294, this mobile number as well. So if you send me a problem or if you scribble something and ask me some clarification, I can solve that and post it as a video format. Okay, but it's important that you work out.